So we'll start with this topic, Wheatstone bridge, and I have drawn the diagram here. The bridge has 4 resistance, and this is a very important circuit because many other things that are analyzed based on such kind of circuit. Suppose you want to find at a time a particular resistance or a ratio of 2 resistance. This kind of circuits are used to analyze many cases. So let's look at the circuit. Here we have the 2 ends, point A and point C, which are connected to the source, and the other 2 ends, they are connected with each other with a galvanometer. Now it has been found that when the current I flows from a positive side of the battery, the current I flows to the point A. Again from point C, the negative current is being connected, and that is how this negative current is flowing in opposite direction, and that is how this current circuit is being formed. So when you have this resistance P and R here, the current I, it divides into 2 parts, which is I1 and I2, and this I1 current passes through P, whereas the I2 current passes through R. So what happens after the I current gets divided into I1 and I2? This I1 passes through P. At point B, it gets further divided into 2, that is Ig, or the current that is flowing through the galvanometer, and the rest of the current flows through Q, which is I3. So we can write from this particular thing that I1 is Ig plus I3 as it gets divided. The second way we can see that this I2 is joined by Ig, and then it flows as I4. So Ig and I4, this together gives me I2, or you can also write it as I4 is equal to I2 plus Ig, right? So in that way you can write I2 is I4 minus Ig, right? So in this 2 equation that we get from the circuit analysis. Now first we look at this particular portion. Since the current is flowing from positive to negative, then let's analyze first this particular part of the circuit, that is A, B, D and A. In this particular circuit, the current should flow in this direction, and the flow is also in this direction. Therefore, my voltage drop across this will be minus sign into I1 into P. In this, again it is flow to the current direction. As we know that towards the current direction, my flow will be always negative. So this will become minus Ig into the potential G, and this particular direction, you will see this is the opposite direction, so therefore this will be I2 into R. So according to Kirchhoff's law, this total current, this total voltage drop and this total for this particular loop will be 0. So this is the first thing that we get from this ABDA loop. Now going to the next loop, which is BCDB. So if we take care of BCDB, this particular loop, we will again see that current should move from positive to negative. Therefore the loop should, the current should follow this particular direction. So I3 follows in the same direction of current, so therefore the voltage drop will be I3 into Q. Then there is a voltage drop, that is I4 into S, which is the opposite direction of the current flow. Therefore, this will be positive, and again there will be Ig into G. This is also positive because this is the opposite direction of current flow. So according to the Kirchhoff's law, this also should be 0. Now a very interesting thing happens, that when all this resistance of the Wheatstone bridge, they are balanced, we call it as a balanced condition. But how do we analyze this balanced condition? A balanced condition is analyzed by seeing or by observing the galvanometer indicator. So galvanometer, if it shows no deflection, it means that there are no current flowing through this galvanometer. Therefore Ig would be 0. It means that point B and point D are at same potential. There are no potential difference between point B and D. There is no current flowing through galvanometer, and then the circuit is in a way that all the resistance are balanced. That is, the current flowing this side, current flowing that side is same. So therefore the circuit is in balanced condition. And to occur this particular situation, let's just calculate how this happens. So if the circuit is in balanced condition, if there are no potential difference between B and D, then we can write for balanced condition or for balanced bridge condition, we have no current flowing through galvanometer, therefore Ig should be 0. If Ig is 0, then this two equation, this two term of this two equation becomes 0. So from this equation, I can write I1P minus I1P plus I2R is equal to 0. So I1, in the place of I1, again I can write it as minus Ig plus I3 into P, plus in the place of I2 I can write it as I4 minus Ig into R is equal to 0. Then taking this, since Igs are all 0, my equation will become minus I3 into P plus I4 into R is equal to 0. Or my I3 into P will be equal to I4 into R, or from here I can write P by R will be I4 by I3. Right? So this what I get from this particular equation. Now taking the second equation, again I3 into Q plus I4 into S will be equal to 0, or I can write as I4 into S is equal to I3 into Q, or I4 by I3 is equal to Q by S. So here I4 by I3 is P by R, here I4 by I3 is Q by S. So therefore equating this two, I can write P by R is equal to Q by S, right? Or we can also write it in another way, P by Q is equal to R by S. So when these ratios of the resistance are in a way, this is the equal ratio, that is P by Q ratio is equal to R by S, or P by R ratio is equal to Q by S, then in that particular condition there won't be any current flowing through the galvanometer. The galvanometer will not show any deflection, and both point P and D would be in same potential, and this particular situation is called balanced situation or balanced bridge situation. Using this particular condition, there are many big or many type of analyzing of the circuits can be done.
If you like the video, then press the like button, subscribe to the channel and press the bell icon.